and mostly thanks to Beppe, because you're invited to a conference from one of your friends, and he puts you first after the social. That's what happens. This morning I was thinking, last time I was at this conference, it was in Rome, and it was in 2018, and I gave the first part of a talk you see today, and I had to spend 12 minutes of my talk to explain to people why we needed antivirals and what were infectious diseases and why we had risk. Something happened in 2019 and 20 that now I don't need to spend all of that time, right? The point is, though, that I want to remind you is that viral infections are a problem that we live with, and they are one of these silent problems. Why they are silent? Because if you look at this graph here, that graph, which it's from 2016, there's basically the same now, nothing changes, shows that communicable diseases, which, just to remind you, they are bacterial, viral, and fungal infection. Communicable diseases are the main cause of death in developing countries. On top of that, you can look worldwide, and roughly half of the people that die of communicable diseases half of the people that die of diseases die of communicable diseases, one half. And so, in a world that was perfectly logical, you would say that one half of the research money in diseases, in drugs, goes to communicable diseases. That's not the case. It's 15%. We can debate why, but there is a very simple reason for that. When it comes to developing drugs, there is a coefficient in front of life. And that coefficient is the buying power of a person that dies. And so, if poor people die, it's less important than rich people. It's as simple as that. I'll give you one number that really, really doesn't make me sleep at night. Diarrhea. There's 1,500 kids, age 1 to 5, that die of diarrhea every day. Most of them die, not all, but most of them, the diarrhea is caused by a virus called rotavirus. Rota and Noro share the first prize. When I started looking into this, I looked at how many groups in the world work in rotavirus. I could find 11 back then. Maybe the number has slightly changed now. In my own university, PFL, there's more than 11 groups that work on cancer. It's just as simple as that. And there's not as many kids that die of cancer than kids that die of rotavirus. Now, we all know that the best way to fight viral diseases is vaccines, no matter what they say on TV or on social media. The problem, though, is that when you get a viral disease, either you have been vaccinated or a vaccine can do nothing, with the exception of rabies. So you need a drug. What you see in this graph here, it's a summary of a lot of the main viruses that attack humans with a condition they give. And the box in violet indicates that we have a vaccine. And you see, rotavirus, we have a vaccine, but people don't arrive to get the vaccine, just to be clear. And in red, there are the antivirals. The summary of this is there's a lot of black. There's a lot of viruses that when you get them, the only thing you can do is just to wait. And if you live in a rich country and the virus is not so big, you wait and you get better. Not in all cases, by the way. If you live in a poor country, you can wait and die. That's our reality, and we live with that, with very minimal funding on this. There is, to the best of my knowledge, no venture capital funding on this. That's the world we live in. The second slide that I used to comment, unfortunately this doesn't work, maybe it's, okay, is this one. So it's the one obvious risk. Since the 70s, there's been a new virus emerging and re-emerging every 4 years. So for the Italians in the room, they know that I was on TV quite often during the pandemics, and they thought I was a prophet because I had foreseen that the pandemic was coming. No, I was born that HIV didn't exist. AIDS didn't exist. I remember the news in the 80s talking about this. I was born that Zika had not taken foot yet. I was born that Ebola had not taken foot yet. I was born that chikungunya was a name that meant nothing. Japanese encephalitis meant nothing, okay? It's every 4 years, there's a new virus emerging and re-emerging. And when they emerge, we never know how they're gonna be. After SARS-CoV-2, monkeypox re-emerged, which is a pretty okay virus, the vaccine worked and so on and so forth, but the next one, who knows? This is a graph of the average lifespan of Americans in the last century. Just, it looks very good, right? Humanity went from 47 to 78 lifespan in 100 years. So every time they tell you, processed food is bad for your health, data don't say that, just to be clear. This dip here, do you know what it is? That's the Spanish flu. That's the Spanish flu, and this is Second World War. And it would look this bad even in Russia, just to be clear. Now, SARS-CoV-2, what has it done? This line is flat here. In 2020, the average world lifespan went down a year and a half. But even worse, this I had not predicted, when in history they plotted world GDP, the richness of the world, 2020 will have a permanent dip there. This is the threat we live with. And just to be clear, the emergence or re-emergence of a virus has nothing to do with hidden labs or things like that, all of the crap you read. It's something that is proportional to the square of a density of a population and the square of a density of the animal-human population. That's it. Nothing more, nothing else. When the Spanish flu arrived, we were 4 billion on Earth. We are 8. You can calculate how more probable it is right now for a virus to emerge. And we have a density of poultry, because we eat chicken, that is unprecedented in history. Basta. This is what we live with. So what's the solution to all of this? The solution to all of it, what is the problem? There's a lot of poor people that need drugs, and there's no money to develop drugs for them. And we need to defend ourselves against a threat that we don't know exactly what it's going to be. So a crazy material scientist born in the south of Italy, so much similarities with Beppe, one morning says, you know what, I moved to Europe, I want to do the equivalent of penicillin. Why do we have a broad-spectrum antibiotics and we don't have a broad-spectrum antiviral? That's what I set up to do in 2010. And, you know, given that I knew nothing about viruses, it took some time to get there, and I haven't gotten there, just by the way. It's not time to make progress. To my surprise, you go in the literature and you find that broad-spectrum antiviral actually is something that people have been looking at, and people are starting to understand that broad-spectrum antiviral can exist since the 50s, basically. And what people understood in the 50s is that viruses target, as a first attachment, a number of conserved glycan on the cell membrane. Glycans on the cell membrane, sugars on the cell membrane, to be clear. These are very few. Why? Because viruses target glycans on our cell membrane we cannot mutate. Otherwise, as humanity goes, we would have already mutated to escape viruses. Because we can also escape viruses. Not only they can escape. But they target heparan sulfate proteoglycan and sialic acid, which is something we cannot mutate. If you take these two, you've done basically 90% of human viruses. And if you imitate one or the other, in vitro, you're going to block all of these viruses. And then you're like, wow, heparin is a drug that was used in First World War as an anticoagulant. We have a solution. Why don't we use it? The reason is that these drugs are reversible. Let me explain this to you. How do these drugs work? First, Look at the viral replication mechanism. I'm not going to comment. Everybody knows this by now. What we do with this drug, we imitate glycans on the cell membrane so that they bind to the virus, and by binding here, they prevent the entry. They are what is called entry inhibitor. This is the way nature does with monoclonal antibody. Same thing, okay? Only monoclonal antibodies, they are not broad spectrum. But these they are. They are also non-toxic, which is very important for an antiviral. We're not talking about the chemotherapy. You need to be non-toxic here, because you're not going to take a toxic thing against your influenza. So now they bind. Everything looks good. The virus doesn't enter, but binding is defined by an equilibrium constant, the dissociation constant, which we give in moles. What does that mean? That when the drug is above the dissociation concentration, you bind. But a good drug must elute, cannot accumulate in the body. At one point it dilutes, it goes down, and when it goes down, what happens is that you get dissociation, and you dissociate into your drug and a perfectly infective virus, then restarts the infection mechanism. So these drugs don't work in vivo, because they protect you for an hour or two, and that's it. That's the issue that you have, and since the 50s, people have tried, have gone to clinical trials, and failed with this approach. But humans are stubborn. You know, still today, you know, I talk with people, they're like, I have this idea to make the binding stronger. How do you make the binding stronger? You make it with multivalency. And you can make it stronger. So instead than 1 hour, your drug is good for 2 hours and a half. You make it 2 times stronger for 3 hours. That's it. That's all you can do. You cannot beat thermodynamics. So then people said, okay, let's actually not make a systemic drug. Let's use this topical in a way that doesn't dilute. And so they made creams against HIV. This went all the way to phase 3 clinical trial and failed royally. Means that the placebo group is statistically better than the drug. Why? That cream attracts virus and binds to virus. It's designed to do that. Now, it works, fine, but if you have a lesion, it's a vaginal cream, the cream gets into your bloodstream, gets diluted, and brings the virus into your bloodstream. So it's a Trojan horse for that. So people keep going, and there is a work that I want to highlight, is the work of Sarit, wonderful work, where she used gold nanoparticles and showed that they are broad-spectrum antiviral. Which was important for me, gave me courage to go in the field. The other thing you need to take home from this slide is to make an heparin mimic, you can put sulfonic acid on natural polymer, synthetic polymer, dendrimer, nanoparticles, anything, it will work. Sulfonic acid or sulfates on anything make a material heparin-like, and they make a broad-spectrum antiviral. Now, I started thinking about this, and the first thing I asked myself is like, okay, but why do we need to do all of this complicated thing? Why do we need to do a drug that's virus-static, what I showed you before? That means that binds reversibly to the virus. Why can't I just go and destroy the virus? Let's go the hard way. Let's make a virucidal drug. Bactericidal antibiotics work very well, okay? So what's a virucidal drug? It's a drug that breaks down a virus. The problem is, the virus is made of the same things we are made of. If you break down the virus, you break the cell together with it. So it's very easy to do a virucidal compound. So you can make alcohol, surfactants, acids. That's why we were washing hands during the pandemic. They're all virucidal. But together with a virus, they break the cell. This is the problem, okay? So unless you're Trump, you're never going to use this as a drug to actually do this. So here comes my idea. I said, okay, fine, let's go back to the drawing board, and let me use a concept that is very familiar for a material scientist. If you're a material scientist trained in the 90s like me, you've taken a lot of course in corrosion. Corrosion is one of the most boring arguments that exist on Earth. But corrosion, it's an electrochemical process, so it's a reversible process, but actually leads to irreversible effects. Because if your bridge falls, there's no way you can anodically make the bridge come back up, okay? So now I said, can I take these beautiful virustatic material that are entry inhibitor, they are broad spectrum, they're heparin-like, they're non-toxic, and can I add something downstream to it that is an irreversible event that makes the process irreversible, keeping the low toxicity? Can I do that? That's the challenge I put to myself. And how do I do that? What my group studies, when I give more serious talk, sorry, this is just inner joke, we study solid-liquid interfaces at proteins. And what I set to do in my career is try to explain why proteins expose hydrophobics to water, which is a very logical thing. But what I know is that there's no folded protein on Earth that doesn't expose hydrophobic to water. I still don't know why. I know now that there are some effects of that. Now, so the protein that binds to the glycan exposes hydrophobic. It's a multivalent protein. In the 80s, people showed this. And so what I thought is that it's also multivalently going to expose hydrophobic by symmetry. So what I thought, I'm going to make a drug that looks like heparin, and it's multivalent. So now, my Italian origin, I need to use my hands now. So I'm going to have a protein that looks for multivalent heparan sulfate protoglycan or sialic acid. I'm going to give it to a protein, and they're going to bind in the equilibrium position. But what I'm going to do is add to my drug hydrophobic tails. Once I bind, there's going to be proximity between the exposed hydrophobic of the protein and the hydrophobics in my molecule. And hydrophobic forces are the strongest one that exists in water, which means that I'm going to have a secondary binding in a non-equilibrium conformation where I'm going to get hydrophobic contact. And this hydrophobic contact will apply pressure on the virus, and ideally, this pressure, repeated by symmetry, will actually break down the virus. So I'm going to start with a reversible event, and I'm going to end up in an irreversible one because by hydrophobic contact, I break the virus. That was my hypothesis. How do you go after it? You go to Sarid literature, which in this field I can recommend, very great papers, and you say, these particles are not very hydrophobic. I'm going to take nanoparticles that are the same, then I'm going to make them more hydrophobic. That's all. I get particles that are highly water-soluble, non-toxic, and then I convince one virologist to talk with me, David Lambo. This is a time where virologists were laughing at me. And we get viruses from the hospital, herpes simplex virus 1, herpes simplex virus 2, papilloma virus, 2 enveloped virus, 1 non-enveloped virus. And we look at the inhibitory capabilities of these particles, and we get nanomolar inhibition. Now, this nanomolar inhibition just means that my particle work like anything else. You put sulfonic acid on things, you get nanomolar inhibition. Okay, now to explain how we move on, I need to explain a little bit about the test we do. First test that we do is a dose-response assay. It's the results of which I already shown you. What we do, we take a fixed concentration of virus. In virology, this is called viral titer. We add different concentration of our compound. We wait, and then we put it on cell, and we measure the plaques, or we measure the RNA or DNA replication. And by that, we get the infectivity. We get the replication of a virus, and the replication of a virus goes down if a drug is a good drug. So when I told you that I'm nanomolar, what I quoted was the EZ50, the half inhibitory concentration, the concentration at which I'm inhibiting half of the infection. From this graph, I can also read the EC99, the concentration at which I'm blocking 2 logs of infection. And here goes the second test. I do a virucidal test, an irreversibility test. I take a virus and nanoparticles and whatever drug you want, okay, at the EC99. So at the beginning, the two samples actually are designed so that their infectivity differs 2 logs. Now, I serially dilute both of them, and I plot the infectivity at the last concentration at which I read infectivity here. If my drug is reversible, I start with 2 log. I get dissociation upon dilution, and I have nothing left. If my drug is irreversible, I start with 2 logs. I end up with 2 logs. So in my graph, in my plot, in my talk now, whenever you see these 2 bars being the same, it's reversible effect. This is irreversible. So now look at this slide. Here I'm comparing heparin, known since '54, to Sarid's nanoparticle that are reversible. It wasn't not in her paper, but they are reversible, and she knew they were reversible, to my particle. All 3 are nanomolar. All 3 pass MTT. Heparin is reversible. Sarid's particle are reversible. Mine are irreversible. And they are irreversible versus herpes simplex virus 2, papillomavirus, RSV, HIV, dengue. So they are broad spectrum irreversible. And we can do more. What I told you in my idea is that I'm putting downstream of binding an event that should lead to breaking. So I can do the irreversibility test at different time points. And you see that irreversibility is something that happens in minutes. I have complete irreversibility only after half an hour, which exactly means that there's a slow event after binding that leads to irreversibility. And then we did TM in the original paper, but let me show you better TM. We do cryo-TM, and what we observe is nanoparticles bind to the envelope of herpes simplex virus 1. This envelope has buddings, spontaneous budding, with and without nanoparticle, but only when there are nanoparticles, the buds become very long, always with trailing nanoparticles. At one point, the bud is so long that it expels the capsid. The protein that binds to heparan sulfate proteoglycan stays here, so the particle keep attacking it, and they break down the virus. And this is what happens to the virus. And that irreversibility will be key for the in vivo data that I showed you later, not the binding constant. And we have plenty of data to show that. So I've done all of this because I want to translate. I want to do drugs, not because I want to do some nice supramolecular things. So this is a test done ex vivo, means that we took vaginal tissue from donors, regrow them at their liquid interface, and what do we show? We see that nanoparticles that have no sulfonic acid have no effect on the infectivity of a virus on this tissue. If we take Sarid nanoparticle, reversible, and we give them at EC99, immediately you block 2 logs of infection. But because you need to feed the tissue, they get diluted. And so 2 days after, 2 days after, half of infection is back, and 3 days after is all back. In my case, it takes much longer to come back. And this is co-treatment, but we can go in pre-treatment, so we give a nanoparticle before and the virus 18 hours later, or we can give a virus and come with a nanoparticle 1 day later, and it still works. At this point, this is the end of a talk that I gave in Rome. I went back to my group, and I asked a very difficult question to ask for people that know me. I came in group meeting, and I said, do we need nano? Okay? And of course, my students immediately said, sure, we need nano, because nano this, nano that, nano magic. But in reality, we don't. And we should learn in our field to ask always this question. What my strategy is, what the invention, if you want, is we need a core, we need multiple linkers, and these linkers are made of hydrophobic tails and binding moiety, right? This doesn't need to be nano. So Sam Jones, that now is a professor in Birmingham, said, okay, I'm going to take a cyclodextrin as a core. It's a natural occurring sugar, is used in deodorant in the US. And most importantly, if you put the same molecule that we put a nanoparticle on cyclodextrin, you get something that looks a lot like this. This is Captisol, an FDA-approved drug as a solubilizer for chemotherapy. So both are antiviral, but this is given to people. It doesn't block any virus because it's reversible. This one is irreversible. And by the way, once we go from nanoparticle to this, the binding constant becomes much lousier, and yet this works much better than picomolar things that exist. Now, it's irreversible in a broad spectrum way, of course. That's the literature teaches that. And once you go to molecules from nanoparticle, there's a lot of classical biological tests you can do. This is the result of a DNA exposure assay that shows that minutes after cyclodextrin got in contact with herpes simplex virus 2, we get release of DNA. That means we break the envelope, we break the capsid, we release the DNA. Just very clearly. Now, you can say, okay, but do you need sulfonic acid? Maybe it's an electrostatic thing and has nothing to do with what you're saying. We did a lot of things to prove that's not the case, but the best thing to do is to just change the moiety. Let's go to the other family, sialic acid. The next pandemic will be influenza. It's not a stupid Italian guy that says that, epidemiologists that know what they're talking about. So let's make an anti-influenza drug. We put sialic acid mimics on cyclodextrin, and we get something that's nicely nanomolar this time against influenza. And we can then, because we have a very precise molecule now, look at the effect of the hydrophobic linkers on this. So we're going to make we made something that has sialic acid, alkanes, cyclodextrin, sialic acid, PEG, cyclodextrin. Both of them are nanomolar. This is irreversible. This is reversible. The irreversible one protects ex vivo. The reversible one does not. Very simple. That's the importance of that hydrophobic group there. Now, the key here is to show you that these things works in vivo, because if not, we go nowhere. And to do that, I'm going to present an experiment done at NIH in the US. It's not that it's NIH or in the US. The important thing here is this experiment is done completely independent of my lab, which is very important in this type of experiments. And the other thing that's very nice is when I called the NIH to do this experiment, they said immediately yes. And then you receive a form you need to compile. The form says mechanism. I wrote virucidal. They call me back, we're not doing it. I'm like, why? Because virucidal molecules are toxic. We don't spend time in testing it. Use this molecule as a disinfectant. I have this in writing. Then I sent them a boatload of data, and they accepted that this thing could potentially be non-toxic, but they allowed me to do the experiment at very low concentration because they were still worried. And here, this is a survival curve. This is an experiment done against H1N1 California 9, the last pandemic strain of influenza. In the placebo, 9 out of 10 mice die. Okay, every group was 10 mice. Normal because it's pandemic. If you give them oseltamivir, Tamiflu, best drugs against influenza, the whole cohort is saved. With my drug, it's 4, 5, and 8 are saved in a dose-dependent way. Notice that the high dose is only 10 times, is 10 times less than oseltamivir. Importantly, my drugs are intranasal, oseltamivir is buccal, okay? Now, this works, so I was allowed to move on. And to move on, I was allowed to increase the concentration, but most importantly, to go to more meaningful experiment, because this is the first experiment every virologist will do, is co-treatment. What does it mean? In the same anesthesia, you challenge the mice with a virus, and you give a drug. It's a non-realistic thing, because you're never going to take a drug in the moment you get infected. So we went in post-treatment. And look at the data here. Placebo group, they all die. So in this experiment, plus or minus 1 is the error. As it's known from the literature, if you give oseltamivir already 8 hours post-infection, the effect is almost completely gone. Only 1 mouse survives against the 10 that survived in co-treatment, or no mouse at all survives. And my drugs save 4, 9, and 10 5, 8, and 9 mice, respectively, all the way to 24 hours post-infection. This is a 5-day treatment. Now we know that my drug can be used only in 2 days, which is the standard for Tamiflu. 2-day treatment is sufficient, and we can go 48 hours post-infection and still save half of a cohort. Why is this? Every drug that works on the virus and the cell changes its efficacy with time because the cell status changes during the infection. My drugs are purely extracellular. They work on the virus, and the virus doesn't change. So I'm very close to concluding here. Let me show you that we can still change the core. And Yong Zhu, that graduated just last week, during his PhD, made a very systematic study in showing that many cores can be used. My invention is very broad. And what we discovered is, because at that time SARS-CoV arrived, let me go, sorry, I'm a bit, that these molecules here are irreversible against SARS-CoV-2, while the cyclodextrin are reversible. And so when we use those molecules, specifically the 6 substituted against SARS-CoV-2 in Syrian hamster, which is the accepted model, we have this result. We have reduction of a virus in the lungs that is comparable and that last day better than Paxlovid. Dimatrivir which is the only FDA-approved drugs against SARS-CoV-2. And in our case, we protect lungs from acute damage better than Paxlovid. Now, there is one thing to say. I showed you that we are better than Tamiflu. In that case, we are better than a good drug. Here, we are almost the same, slightly better than a drug that's not that great. So we're still not great against SARS-CoV-2. And I'll conclude here thanking the people that have done this, or my past and current group, thanking my funding agencies, mostly the Werner Siemens Foundation, that has been so generous in funding me, and thanking you for your attention.
Thank you very much. Really interesting talk. Questions from the audience? We have some there.
Francesco, great. One of the main mechanisms of action you show is the hydrophobic interaction between your linker and these magic patches of proteins that show to the outside. But in your whole talk, you don't really focus on engineering the hydrophobic linker part.
Oh, I have not presented that. We have a system.
No, wait. Let me. I'm sure there's work, but the question is, how much is the valency of these multivalent linkers important? Because every protein must have the valency of your linkers directly matches to the amount of hydrophobic patches on your protein.
So, the systematic study that Young did clearly showed that the valency matters for a binding constant. The hydrophobic does not need to be valent, multivalent, as long as it's enough. So you don't, you need at least 2, so you can say you need multivalency. But for example, you don't need all 6 arms to be hydrophobic. You need at least 2, I think, to apply this pressure that you have, and you need enough. So you can have 6 arms that are C6, and that works, or you can have 2 arms that are C12s, and it works also, you see. The hydrophobic is more of a question of how much hydrophobicity can you bring close to the virus. And just to be clear, when you're making a drug and you want it low toxicity because it's an antiviral, it's not a chemotherapeutic, you know, you need to keep the solubility of your molecules impeccable. Otherwise, you start having all sorts of side effects. So you add hydrophobic, but you also need to engineer the molecule to be soluble. So we've tried many other cores, and okay, they work, but they're so insoluble that at the end, there's all sorts of side effects.
And are your linkers always flexible? Have you looked into some
Yeah, so we did a study, only one study here, where we compared alkanes to benzenes, chains of benzene. The chains of benzene don't work. So in that case, they're rigid and it doesn't work. Can you do something in between? Probably yes, I don't know.
That's good. Thank you very much. I'd like to see always the update of this. Since 2018, I remember. It was quite a nice introduction. And I think
but it was tough. My work started in 2010. I started understanding something in 2013. The mess disappeared in 2015. And only from 2016, data.
And it's actually a good example of how you can actually make medicine using the same principle of nanotechnology, using not just simply drug delivery and gene delivery, but actually the construct itself is a drug. That is one thing I share with you. Now, 2 questions here. The fact you have this hydrophobicity requirement, and you call it pressure. I think you probably get eporation on the membrane. You kind of is it possible that you act as like a local surfactant?
We break the envelope, and that must be for some form of poration.
Yes.
But we break the capsid too.
Okay.
And that's where the pressure counts. And we have molecular dynamic simulation that show that.
Yeah.
Now, we don't need to break the capsid, unless it's a non-enveloped virus. But we do.
Okay. But the capsid breaks because you break the envelope, or breaks because of your particles?
No. Those viruses are perfectly stable without envelope.
Okay, right. And then going back to your latest data with the SARS-CoV-2, then I know you're upset, so you don't like to, because one thing, at least as far as I know about viruses, that one of the biggest difference going from influenza to SARS, I don't know the other viruses, is that the amount of spike protein, so therefore your receptors in your case, is considerably different. The SARS-CoV have much less receptor than...
and that's why we need to use a stronger hydrophobic drug to actually break it down, because by symmetry we repeat less.
Or more ligands.
Or more ligands, maybe.
Yeah. So you can play with the multivalencies and perhaps the size.
Perhaps. You know,
because
we've tried many things against SARS, you can imagine.
It's very tiny, right?
We tried many things against SARS.
Okay.
Only 2 things have worked. One in collaboration with Rainer Haag, where we get pre-assembly and we make a supramolecular thing that goes there massive, which is great. But in vivo, it didn't work as well as a simple small molecule. The other thing, when you design drugs, what you learn, simpler is better, right? A benzene, 6 arms, it's 1 molecule, FDA approval is very simple, it's not a mixture. When you want to design drugs, simpler is better.
And the other difference I remember is actually that SARS-CoV-2 doesn't have a capsid, or it has a very...
it doesn't have a capsid. Once you break the envelope, you're done there.
Exactly.
All you need to do. But it's a fairly stable envelope. Even in terms of surfactant, you need to add a lot to break SARS-CoV-2, because it's super glycosylated. Glycosylated.
Yeah, thank you, Francesco. I had a follow-up question.
Yes, okay.
It's a follow-up question that I had in the different molecule that you use, and at the different concentration that you are. Do you always present to your virus a molecule or an assembly of molecules? And how does it influence? Because then the surface contact from your
we measured accurately the CMC. When we can measure it, some of these things don't have a CMC. The nanoparticle don't have a CMC. But we measure accurately the CMC, and the concentration we use are 100 to 200 times lower than the CMC. Now, that guy behind you, the crazy Italian guy, one time said, okay, but what if the virus is a catalyst for aggregation? This may be, I don't know. It remains to be seen. But what arrives to the virus, we've done extensive cryo-TM studies, us and in Germany. What arrives to the virus is a single molecule. What happens once you bind there remains to be determined.
And would you imagine something that is self-assembled a bit bigger, and then restructure and reconfigure?
This is what we're doing with Rainer, that it self-assembles, it does that, absolutely. Absolutely.
Thanks for your presentation. I have a question regarding the point of action of the drug, as in you know that like some antiviral drugs, they can be used as pre-exposure prophylaxis. Do you see a potential in your drug to act like in a preventive way?
So there is that potential, but honestly, I'm not a believer in drugs for prophylaxis. The better prophylaxis against the virus is a vaccine. There is no comparison. A good drug must elute from your body. So we'll stay there 4, 5, 6 hours. And these drugs are drugs that you should take 1, 2 days and be done with it. You start, if you're a nurse and you're starting taking them every day for your life, who knows what side effects you can have. It's still an heparin-like thing, right? So there is a prophylaxis against virus. It's called vaccine. So maybe, you know, there are some viruses and for some jobs where this can be used, but I'm not a believer in that use of drugs.
Yeah,
drugs are good. You know, what I'm showing you is it works 48 hours post-infection in a mice. A mice infection is 3 times faster than a human. That means that you take an influenza, at day 4-year-old, you start feeling sick, you can start taking the drug. That's how you use a drug, right?
Yeah. No, of course, like I was just asking in case like maybe the vaccine can't be found. Like in
See, if a vaccine can be found, yes, absolutely.
Right. Thank you.
Okay, okay, we'll take the last question because we have to move on, but there's one in the back.
A fantastic journey of presentation. I was wondering, is the drug, have you tested the drug as a virucidal, but for textiles or for surfaces, for coatings? Will that work?
So we have strategies to make textile virucidal. Of course, you don't need this complex thing because once you make it for textile and other things, the condition of low toxicity and solubility, so keeping the hydrophobicity in check, you can remove it a little bit. And so, yes, it can be used. We have strategies to have these drugs and reload the textile constantly with these drugs. Absolutely.
But it is an overkiller then in this?
Okay.
No,
but there are simpler molecules we can talk to side that we've designed that work for textile and for other things.
Thank you.
Okay, we have to move on. Thank you again, Francesco.